Okay, welcome again. We will be continuing with Internet of Things Embedded Systems and System Processing Part 2. GPIO pins are the gateway between your Raspberry Pi and the physical world, allowing you to connect and control various electronic exponents. And this is something we have explained before in the previous, in part 1. As a quick reminder, the Raspberry Pi has 40 pins header, many of which are general purpose I/O pins. These pins provide the interface for your projects. To start using GPIO pins, the first step is to include the library. This is done by adding the line import RPi.GPIO as GPIO at the beginning of your Python script. This line imports the necessary library for interacting with GPIO pins and assigns it the alias GPIO for easier use. Next, you need to set up the use of the to set up to use the pins. This is done using the GPIO set mode function. You have two options. The first option is GPIO.BOARD or GPIO.BCM. GPIO.BOARD refers to the physical pin numbering on the header. This means you refer to the pins by their physical location on the board. GPIO.BCM refers to the Broadcom SoC channel numbering. This means you refer to the pins by the channel numbers assigned by the Broadcom processor. The choice between these two modes depends on your preferences and the specific requirements of your project. This slide specifically explains the GPIO.BCM mode, a common and often preferred method for referencing GPIO pins. As you can see, the GPIO.BCM option means that you are referring to the pins by the Broadcom SoC channel number. These numbers are the ones labeled after GPIO in the green rectangles around the outside of the diagram. For instance, GPIO2, GPIO3, GPIO4, and so on. This mode refers to the pin numbers as defined by the Broadcom processor on the Raspberry Pi. When you use GPIO.BCM in your Python code, you directly referencing these Broadcom channel number. This mode is often preferred because it's more consistent across different Raspberry Pi models and revisions. Understanding GPIO.BCM numbering is crucial for accurate and reliable control of your Raspberry Pi GPIO pins. This slide presents a clear diagram of the Raspberry Pi Raspberry Pi's 3 GPI header outlining functions or the functions of each pin. As you can see, this is Raspberry Pi 3 GPIO header, providing a comprehensive overview of the pin functions. As we can see, the table lists each pin number and its corresponding name, providing essential information for connecting components. The pin number column indicates the physical pin number on the header. The name column describes the function of each pin, including GPIO numbers, power, ground, and alternative functions. The color-coded circles next to each pin name provide a quick visual reference for each pin's function. You have 3.3 V DC power, and you have DC power 5 volt pins for powering your circuits, as we can see here. Multiple ground pins are available for grounding your circuits. The GPIO pins are the general purpose I/O pins that you can use to connect sensors, actuators, and other components as we described before. Some pins have alternate functions such as I2C, SPI, UART, providing additional communications options. The ID, SD, and IDSC, these two, are used for I2C, ID, EEPROM communication. So this diagram is provided by Element 14, as we can see this website, a reliable source for Raspberry Pi information. In this slide presents a simple Python script that demonstrates how to configure and use GPIO pins for input and output. Let's start with the input section. Here we are configuring a resistor connected to GPIO pin 22. We first define a variable, my sensor, you can call it whatever, and assign it the value 22, which represent the GPIO pin number. Then we use the GPIO setup function to configure pin 22 as an input. This is how we configure it as an input. The GPIO argument specifies that this pin will be used for reading input. Next, we use if statement to check the input state of pin 22. The GPIO pin dot input function, or the GPIO.input function reads the current state of the pin. If the input is high, meaning the sensor is active, the script prints sensor activity detected. Now let's take a look to the output section. Here we are controlling an actuator connected to GPIO pin 23. We defined a variable, my actuator, and assigned the value 23, representing the GPIO pin number. We use the GPIO dot setup as a function to configure pin 23 as an output. Like I said before, in context of GPIO.in, GPIO.out argument specify that this pin will be used for sending output. Finally, we use the GPIO.output function to set the output state of pin 23 to high, which turns an actuator on. The true argument represents a high output. This is the true argument. This slide outlines the key differences between these two approaches and prompts us to consider their examples, pros and cons. Let's start with non-blocking operations. As this slide says, a non-blocking operation gets a value and keeps going. This means the program does not wait for the operation to complete before moving on to the next task. Consider examples like checking the status of a sensor without waiting for a response, or sending a network request without waiting for a reply. Non-blocking operations offer benefits like increased responsiveness and concurrency. However, they can also introduce complexity in handling asynchronous results and managing resources. Now let's look at blocking operations. In contrast, a blocking operation waits until an event occurs. This means the program pauses its execution until the operation is completed. Examples include reading data from a file, waiting for a user input, or waiting for a network connection to be established. Blocking operations simplify program flow and data handling, but they can also lead to performance bottlenecks and unresponsive applications. This slide presents Python code that demonstrates how to use callbacks to respond to events on GPIO pins. Let's start with the first line. Here we are configuring GPIO pin 23 as an input. The pull up down equal GPIO.POD underscore up argument sets an internal pull-up resistor, meaning the pin will be high by default and go low when an event occurs, like a button press. Similarly, we are configuring GPIO pin 23 as an input, but this time with a pull-up down equal GPIO.POD PUID down argument. This sets an internal pull-down resistor, meaning the pin will be low by default and go high when an event occurs. Next, we define a callback function called myCallback. This function will be executed when an event occurs on pin 24. This is where we call the function. In this example, it is simply prints event detected. Finally, we use the GPIO.add detect function to set up an event detection on pin 24. The GPIO.rising argument specifies that we are looking for a rising edge, meaning the pin going from low to high. When these events occur, the myCallback function will be executed. This approach allows the program to continue executing other tasks while waiting for events, make it more efficient and responsive. This slide focuses on the output capabilities of the Raspberry Pi GPIO pins, demonstrating how they can be used to control simple circuits. As you can see, GPIO pin outputs are 3V3 or 0V. Can be called. This means the pins can provide either 3.3 volt signal or a 0 volt signal, representing high and low states respectively. These states can be called on or off, high or low, and each pin can turn on and off independently. This allows you to control multiple devices connected to different GPIO pins. Let's look at an example use case. In this diagram, we see Raspberry Pi connected to a lid through a resistor. The resistor is used to limit the current flowing through the lid, preventing it from burning out. The circuit diagram at the bottom shows a simplified representation of this setup. The Raspberry Pi acts as a switch, controlling the flow of current from the 3.3 volt power source to the lid. By setting the GPIO pin connected to the lid to high, which means 3.3 volt, we turn the lid on. Setting it to low turns the lid off. This slide focuses on the input capabilities of the GPIO pins and introduces the concepts of pull-down and pull-up circuits. As you can see, GPIO pins are the simplest I/O on microcontrollers. They provide basic way of microcontroller to interact with outside world. A crucial aspect of using GPIO pins as inputs is understanding pull-up and pull-down circuits. These circuits give an input pin a reference, ensuring a stable and predictable input state. Let's look at the pull-up circuit first. In this configuration, a resistor connects the GPIO pins to the VCC or power supply here. This ensures the pins is held high by default. Now let's look at the pull-down circuit. Here a resistor connects the GPIO pin to ground. Here. This ensures the pin is held low by default. For example, if you connect a switch to GPIO pin with a pull-up resistor, the pin will be high when the switch is open and low when the switch is closed. Conversely, with a pull-down resistor, the pin will be low when the switch is open and high when the switch is closed. In this slide, we outline the key properties of LEDs and how to connect them correctly. As you can see, when you pick a LED, you will notice that usually one leg is longer than the other. This is a crucial physical characteristics that helps identify the LED polarity. The longer leg, known as a node, is always connected to the positive side of the power supply. The shorter leg, known as the cathode, is connected to the negative side of the power supply, often referred to as a ground. Importantly, LEDs will not work if power is connected the other way around. This means the polarity must be correct for the LED to function. The symbol in the left represents LED in a circuit diagram. The arrows indicate the direction of the current flow from the A node to the cathode. The physical LED on the right shows the longer A node leg and the shorter cathode leg. This one. Let's talk about resistors. So resistors, they have a vital role of in electronic circuits, especially when working with devices like the Raspberry Pi. As you can see, resistors are used to limit the amount of electricity going through a circuit. The measure of resistance is called OHM, represent the Greek letter omega. The higher the resistance, the more it limits the current. The Raspberry Pi can only supply a small current, about 60 mA, which is milliamperes. Milliamperes. MA stands for milliamperes. This is why you must always use resistors to control LEDs to the GPIO pins of the Raspberry Pi. LED will want to draw more current than the Raspberry Pi can safely provide. If allowed to, they will burn out the Raspberry Pi. By adding resistor to the circuit, you ensure that the current flowing is less than 60 milliampere. This will prevent the damage to the PI. This image shows a typical resistor, and the symbol below it represents a resistor in a circuit diagram. In this slide, we are demystifying the color code used to determine the resistance of resistors. This slide explains how to read the 4-band resistor color code, the most common type you will encounter. As you can see, most common resistors use 4-band resistor code. The table shows the colors and their corresponding numerical values, ranging from 0 to 9. The first 2 bands represent the first 2 digits of the resistance value. The third band acts as a multiplier, indicating the power of 10 by which the first two digits should be multiplied. The fourth band represents the tolerance, indicating the accuracy of the resistor's value. For example, if a resistor has a band has the bands brown, black, red, and gold. The brown band represents 1, the black band represents 0, the red band represents a multiplier of 100, and the gold band represents a tolerance of a plus minus 5%. This means the resistor have a value of 1000 OHMS or 1 kilo HM with a tolerance of 5 plus 5 minus percentage. This slide provides two examples to illustrate how to determine the resistor values from the color bands on a resistor. This is additional example. So let's look at the first example. We have a resistor with yellow, purple, and red bands. Yellow represents 4, purple represents 7, and red represents 10 to the power of 2, or 100. Therefore, the resistance is 47 times 100, which equals 4,700 OHMS, or 4.7 kilo HMS. Now, let's look at the second example. We have a resistor with brown, black, and brown bands. Brown represents 1, black represents 0, and the second brown band represents 10. Therefore, the resistance is 10 times 10, which equals 100 OHMS. As you can see, OHMS law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. This relationship is expressed by the formula V equal IR, where V represents voltage, I represents current, and R represents resistance. So let's look at an example. If we are passing 5 volts through a 330 OHM resistor, we can calculate the current using OHM law. Regarding the formula to solve for current, we got I equal V divided by R. Plugging into values, we get I equal 5 divided by 330, which equals to 0.015 amperes or 15 amperes or 15 mA or milliamperes, 15 milliamperes. Rearranging the formula to solve for the current, we get So let's take a look to the circuit diagram. So this circuit diagram illustrates this relationship, showing the voltage across the resistors, and the current flowing through it, and the resistance value. Jumper wires. This slide explains what jumper wires are and the different types you will encounter. As you can see, jumper wires are used on a breadboard to jump from one connection to another. They provide a convenient way to connect components without soldering. These wires can have various connectors. Typically, they have ends with pins that go into the breadboard, known as male connectors, or ends with a piece of plastic with a hole in it, known as female connectors, which fit onto GPIO pins. Let's look at the different types. Male jumper wires are used to make jumps on the breadboard, connecting different rows and columns. Female jumper wires are used to connect GPIO pins to the breadboard, allowing you to interface with a microcontroller or development board. Female to female jumper wires are used to connect components to each other, such as connecting a resistor to a LED. This image illustrates these different types of jumper wires, showing their various connectors and applications. As you can see, the diagram shows a Raspberry Pi with its GPIO pin labeled. We are focusing on connecting a LED with a resistor to these pins. The circuit includes a LED, which is a light emitting diode, and a resistor. The resistor is crucial for limiting the current flowing through the LED, preventing it from burning out. We are connecting the resistor to the 3.3 volt power supply. The other end of the resistor, so this is the other end of the resistor is connected to the longer leg of the LED. So this is the longer leg of the LED, known as the A node. The shorter leg of the LED, known as a cathode, is connected to the to the ground, to the G and D pin, which provides the ground connection. So this is where it shows the ground connection. When the circuit is complete, the power is supplied, the LED should light up, indicating the circuit is working correctly. So this is, this is a very simple example where we have connected everything, and where we can do some testing. Please work in these tasks: task 1, task 2, and task 3, and task 2 and task 3. There is an initial work that has been done for task 1, so please continue working in task 1 and task 2 and task 3 as part of testing and part of the exercise, work with Raspberry Pi. And thank you for listening, and see you in another lesson.